Hello everyone, my name is Tully and my partner is Seth. Today we want to talking about the manifestation of the uniform random number. This is chapter 2 in the textbook Simulation and Monte Carlo with the application in finance. So first of all, I want to go overall the chapter. What is the chapter 2 talking about? The chapter 2 says try to proving that after you generate after an amount of the time when you generate a random number, it's gonna repeat. So the first section in chapter 2 is named linear congruential generator, and on the top of the screen here you can see this is the whole function we're gonna use, and this function gonna prove that it's the generate random number gonna repeat after an amount of time. And the reason why we're using mod m here is because we don't want to generate a random number with a zero value. So the x1 here stands for the 6, which means initial value. The 8 is the multiplier, which have to be greater than 0, and the 6 gonna be your add-in, which means have to be greater than 0 too. M here stands for the modulus, which means solve for the remainder of the division. And xi is the range is gonna be from 0 to m minus 1, which means the maximum of the xi is gonna be the value of the xi gonna be, so the period first number is I, where xi is equal x0, which means the first period. The best results if C and M have no common factors. The second thing is A minus 1 have a primary factor from M, and the last one is A minus M is a multiplier of 4. Next chapter we have a mixed linear congruential generators. So in here we have C always greater than 0, and M gonna equal 2 over b minus 1, which means b is the number of computer bits. In here set is a really high number, which means usually we're gonna use 2 over 31. And from when we use with the really highest value of m here, the result gonna show us it's very repeat after really long, more than 2,000 times or a lot of time when you generate random number. The next section in this chapter 2 is the multiplicative linear congruential generators, and it's quite the same with the previous chapter, which means the mixed linear, and in here it have the same condition, which the only difference here is that m is derived for the maximum periods, and a is the primitive root of m. So in here the lambda is going to be smallest integer that makes m is a prime. Last session in this chapter 2 is the theoretical test for the random number. There are 3 types of generator, which means lambda is equal periods. The first generator type is the full period of multiplicative, and in here the m gonna equal 2 over b, a is gonna equal 1, mod is gonna equal 4, c is gonna be the odd integer, and lambda gonna equal with m. The second type of this is the maximum period multiplicative prime modulus, which c is going to equal 0, lambda going to equal m minus 1, which m is the primes, and a is the primitive root of m. The last one, maximum period multiplicative, which m is 2 power b, a is equal 5. The most going to be a times for lambda is also equal m divided by 4. And the last section in chapter 2 is how the problem gonna happen with when you increase the last problem is gonna be problem with the when you increase the dimension when you generate a random number. So it's gonna be happen when you have something when you generate number with more than 2-dimension numbers. So in order to solve this problem, they have to shuffling the randomly generate number, and they have to compile the generators. And that's it for the chapter 2. I'm going to show you how we coding this into the MATLAB. So this is the homework problem that we did for the class. When we run this, you can clearly see that the feature 1 is solved. The X, B gonna show the correlation between A and B when you generate random number. So it's gonna be repeat after an amount of the time, and it's gonna be followed increase after an amount of the time. That's it. Thanks for watching.